Okay, and I'll let you take it away.
Okay, thank you for having me here. I am Meg, and I just completed my dissertation in June of last year. And thank you for this opportunity to share my research work with all of you. I will start by introducing the data set that I've been working with. The global atmospheric chemistry data for 1 year is simulated by a GEOS-Chem chemical transport model, or CTM, that seamlessly integrates with the GEOS-5 Earth system model. The data was provided by Dr. Christoph Keller, who works at NASA GSFC. And this model is, I think, open source. So this is the data that I have done all of my work with. This is my starting point. In this work, we are specifically concerned with the time series measurements of the concentration of chemical species collected from spatial locations in the atmosphere. So we form our data matrix by stacking all the spatial cells in a column, and each column represents the snapshots in time. So this is a typical way we form data matrix. The year-long simulation data is exceptionally high-dimensional and massive, and applying dimensionality reduction techniques first required careful considerations of pre-processing the data. First, we did an efficient slicing and reorganization of the data, isolating the data sets of interest. And then, very importantly, we had to factor out the translational invariance in the data. So the time series for each grid cell is aligned with the GMT time, because SVD-based approaches do not do well with the temporal invariance. We worked with 6 chemical species and 2 variables for each species. The chem start variable, which is the absolute concentration at the start of a time step of the chemical species, and the chem 10, which is a rate of change of concentration. These were of interest to Dr. Keller. The first part of my work is developing scalable diagnostics using the Ristretto library. So by exploiting randomized linear algebra algorithms, a suite of decompositions are proposed to extract the dominant features from the big data sets. Sorry, I'm just referring to my notes in case I forget something. So we use randomized linear algebra methods here to extract the dominant low-rank features from a full 3-dimensional data set of atmospheric chemistry. These methods are highly scalable. They scale with the intrinsic rank of the global chemistry space instead of the measurement space, and hence they are computationally tractable, and they can also be used to enable efficient representation and compression of the data. Let me lay out the probabilistic framework briefly. So assume that our data matrix X has an intrinsic rank, which is much smaller than the measurement space. The basic idea of the probabilistic algorithms is to employ a degree of randomness in order to derive a smaller matrix B from the much larger data matrix X. None of the non-randomness should obscure the dominant spectral information that is present in the data, as long as the original data has some low-rank structure. Then a deterministic algorithm can be applied to the smaller matrix B to compute the decompositions. Several probabilistic strategies have been proposed to form the smaller matrix B. We use the Halco method, which is called a QB decomposition, which decomposes the input matrix X into an orthonormal column matrix Q and the much smaller matrix P. So here K is the desired rank that I want to truncate to. So here the first stage is to build the matrix Q. So what we do is we use random projections to sample the column space of the input matrix X. These random projections are denoted by sigma, omega, and we construct this random matrix by first drawing a set of Q independent random vectors from, say, the normal standard normal distribution, and then mapping X to the low-dimensional space, or to this low-dimensional space to form this the sketch matrix Y, which is the random projections. Then we autonormalize the columns of Y to compute by computing a QR decomposition. The Q is the near optimal low-dimensional basis that provides the column space of the input data matrix X. Then in the second stage, we build B by restricting the high-dimensional input matrix to the low-dimensional space. And this is a projection geometrically that takes points in a higher dimension and projects them on a lower dimensional space while maintaining the structure in a Euclidean sense. Now we can use the approximated B to, instead of the input data matrix X, to compute the traditional deterministic matrix decompositions for the analysis of the data. So one of the decompositions we studied was the SVD, randomized SVD decomposition, where we again compute the factors U, sigma, and B from B, and the higher dimensional reconstruction of U can be obtained by its lower rank representation U tilde. And we compute the energy spectrum of the data using the singular values. So here we have presented, for instance, the data diagnostics for ozone, which is a challenging compound for chemistry models. We find that despite the underlying complexity of the chemistry, the ozone concentration fields produced by GEOS-Chem exhibit prominent low rank features. Here presented on this figure is the energy spectrum of the data. These are the temporal modes, the first 4 dominant temporal modes, and these are the spatial modes, first 8 spatial modes at the surface of ozone. So from the energy spectrum, we can see that 150 modes captures about almost 100% of the energy of the field energy. And inset here is the zoomed in figure of the first 10 dominant modes, and I have highlighted the first 4 here, color coded, and these are the corresponding temporal modes for those 4 singular values, dominant singular values. And the geophysical interpretation of these modes is easiest when combining the temporal pattern with the corresponding spatial features. So the surface ozone exhibits distinct seasonal patterns, as can be seen from the temporal modes. The first mode, which is shown here, resembles the annual average surface concentration of ozone. It can be seen as interpreted as a time invariant. The blue line is the corresponding temporal mode. Time invariant average ozone field from which all other modes subtract or add to describe the spatio-temporal variability of ozone in greater detail. Modes 2 shows a distinct gradient at the equator, and as well as a distinct pattern over the northern hemisphere urban regions, as well as the southern hemisphere regions. So the seasonal variability of a mode, which is peaking in August or the summer, is consistent with the fall observed ozone burdens, and ozone is known to increase during the summertime in the urban regions due to increased photochemical activity. And mode 3 is additional forcing to mode 2 because its seasonal variability is approximately the same, and it shows dominant features over the polluted regions of Eastern China, Europe, and America. The most dominant feature of mode 4, for example, is the pattern over Africa, and this has the purple line has peaks around July, August, and January, February, and this corresponds to a known biomass burning activity in Africa during those 2 seasons. And so we show here represented decomposition method successfully extracts the major features of the ozone tropospheric chemistry. Here. Next, furthermore, we can use the approximation matrix B for efficient compression and storage of the data. The compression advocated here is achieved by producing a low-rank representation for constructing the high-dimensional data, so it should not be confused with traditional standard data compression algorithms. So a fraction of data needs to be stored. We need the matrix Q and our embedding columns of U tilde, sigma, and V. That's all we need to store. And we can compute the high-dimensional reconstruction of the data using its low-rank representation. Low-rank representation, for instance, we show a reconstruction of the absolute concentration of surface ozone at a randomly selected time. And so this is the actual data, and this is a reconstruction using just 5 modes, 50 modes, and 100 modes. These reconstructions require only storing 0.025%, 0.25%, and 0.5% of the data, respectively, as opposed to the 87 million data points of the original annual surface ozone data. The reconstruction is as few as 5 modes already shows some of the dominant features being captured. And the reconstruction using 50 modes and 100 modes is practically no difference. So this simple example shows that the compression of modes using our randomized architecture can serve as critically enabling tool for the storage of numerical simulations and atmospheric chemistry data, with compression rates up to 1,000-fold. Now I move on to the second part of my research work, which is optimized DMD for forecasting and reconstruction of the data. Computationally effective and adaptive reduced order model approach is embodied by the DMD. It is a leading data-driven regression architecture for directly learning linear dynamics over snapshots of temporal data in a low-dimensional space. And here I'll demonstrate that the optimized DMD or the OptDMD version of the DMD algorithm is critical for characterizing the complexities of the chemistry dynamics. If I have time, I'll go over quantifying the temporal uncertainty in the models that are quantified using BOP-DMD or bagging optimized DMD. So the DMD decomposition is expressed here in the first equation. And the optimized DMD, instead of using a linear regression, uses a variable projection method for solving the nonlinear least squares problem, exponential fitting problem, where sigma b is sigma times the diag b, the spatial components. And this has been shown to provide a superior decomposition due to its ability to optimally suppress bias and handle snapshots collected at arbitrary times. As an example of how effective the optimized DMD is, I present a 40-day reconstruction results for OH hydroxyl ion for both the start data and the tendency data. On the top panel here is the actual data. So I had to restrict to 1 latitude at a time because I need consistent daytimes for the DMD analysis, for effective DMD analysis. And this is for latitude 30 degrees, all the longitudes, and for 40 days of time. That's the actual data. When we used a classic DMD, which is the first thing I used, I got nothing. It was not able to capture any of the dynamics of the original data. And this is because most of the eigenvalues were lying on the negative real axis. So I just had dying off modes. So this was a major turning point in my research when I applied the optimized DMD without any constraints, and I found that it was able to faithfully represent the features of the actual data. And this is just using 25 modes for the start data and 50 modes for the tendency data. And the eigenvalue spectrum on the left here shows that there are still some eigenvalues on the positive rear on the right-hand plane, which will indicate exponentially growing modes with time. So while this is a good method to reconstruct the data, it will not be effective in forecasting the data well. So we moved on to constraining the eigenvalues to be on only the left half plane. Here we did get an accurate reconstruction as well as good forecasting abilities of the data. So this is the approach that we'll be using throughout this work. We also played around with constraining only to the imaginary axis, the eigenvalues, to get purely oscillatory modes, and those were not able to capture the dynamics either. Using the optimized AMD with constrained eigenvalues, I computed the relative error, reconstruction mean error, and as we expect, we see that as we increase the number of modes, the error elbows out or that goes to a plateau. And some of these spikes are because we are solving a nonlinear optimization problem. So sometimes it fails to converge to a solution. So we see these spikes, but overall, we can see that the error is dying out as we increase the number of modes. Also, the tendency data requires more modes to capture its dynamics as compared to the start variable. Here I have presented the reconstruction and prediction data, forecasted data results for 6 longitudes in that one latitude, 30 degrees. Here are the time series presented for the actual data. The black dotted line is the actual data line for both the tendency and the start data. The pink line is the reconstructed line, as usually we can see in the eyeball measure, eyeball norm, that it fits the original data very pretty well for both the tendency and the start data. And then we start a prediction window where we reconstruct the time snapshots that have not been seen by the optimized DMD algorithm. And we can see that in the eyeball norm, again, it does a pretty good job predicting for the next 20 days what the time series would be. And here in the tendency data, you can see that we have used less number of modes, only 50 modes. So it's not able to capture the peaks very faithfully, but it does the best it can. So the mean errors for the 20 days of data that I had, I just wanted to see if I go away from the last reconstruction snapshot, is my test data going to test error going to get worse as I go away further from it? And it does not. For most of the chemicals, it remains pretty steady across the 20 days tested. Again, tendency data needs more modes to represent it. Therefore, the errors there is higher, and we see the highest errors for 2 of these chemical species, the carbon monoxide tendency and the OH start data. But it does pretty well, and I could further quantify the temporal uncertainty in this DMD models by using the BOP DMD. If I again have time, I'll come back to that. And the last part of my research work is data-driven sparse sensor placement for reconstruction of the data, original data. The optimal sensor replacement determines placement of sensors in a complex evolving system to optimize several downstream objectives, such as full state reconstruction from just a few point measurements or prediction from just a few point measurements. So the instantaneous reproduction of atmospheric chemistry data in this work is based on combining 2 key techniques. One is the machine learning, which exploits the patterns in the data for low-dimensional representation in a tailored POD basis. And the POD learns from the atmospheric surface atmospheric chemistry. Here I have restricted to the surface just to pick one elevation. And I have also cut out the poles because they were skewing my results by a lot. So we are looking at 33 latitudes and all the longitudes at the surface. So it the tailored library of POD basis functions provides a compact representation of the high-dimensional chemistry at the surface. And the second key technique is we reconstruct the full state from a small subset of measurements. I'm sorry. I have a sore throat, so it's dying out. We reconstruct the full state from a small subset of measurements from optimized sensor locations. So we carry out principal design of highly specialized optimal sensors using QR pivots. And these two techniques enable us to recover the full signal in the POD basis from a small subset of point measurements. So first, we compute the reduced SVD of the data matrix, truncating at a desired rank R. This truncation, where to truncate is often a difficult question. And here we have used the recent work by Gavish and Donovan that provides an optimal hard threshold based on the singular value distribution of the data as well as the aspect ratio of the data matrix. That's where we truncate at. And the POD basis modes are, I will be designating as sigma R from now on. The low rank representation of the state can now be expressed as pi r times A, where A is the sparse vector indicating which modes are active. For time series data, these are time varying. And these are the spatial, this is the spatial mode. So they are separated the spatial and temporal modes here. The goal is to design the point matrix C, sampling matrix C, where P is a small number of point measurements. The point measurement structure, the measurement matrix C as this, where gamma indicates where the sensor is placed and the rest of the entries are zero in C, the columns of C. So we find our measurement Y by applying C to X, that is applying C to phi R times A. So giving us this theta A matrix. So now we can, now we can have an accurate reconstruction of the full state by inverting that matrix theta. And I denote the matrix to be inverted theta as M. Here I have shown two different cases. One is when the point measurements that we are, the sparse sensors that we are placing is equal to the number of modes that we have used to truncate the POD. And the second case is oversampling, where the number of sensors are greater than the number of modes I'm using in the POD reconstruction. So I have to invert this data, this matrix, the optimal sensor locations that enable the best possible reconstruction, that is select the roads or phi r that optimally condition the inverse. And with QR factorization with column pivoting provides an approximate greedy solution to this optimization problem. This is from discrete empirical interpolation methods. So this matrix can be computed. Now the sensor locations can be computed from our phi r matrix. Let's move on to the next slide. I'm not sure what's happening here. It's frozen. Can someone help me? It's not letting me do anything.
Okay. Let me see if I let me stop your sharing, see if that will that reset it? Is your computer still frozen or is it okay now?
No, it's okay now.
Okay. Now I think you can share again.
So, so we have constructed our optimal sparse spatial locations, sensor locations, sorry, in space. And now we're going to see how well they perform. So we implement the QDEIM for sensor placement and its extension, the oversample case. For the star data, we are truncating at 50 modes, and for the tendency at 50 modes. For I'm sorry, I've lost track. Okay, so here I have the actual data set that at the surface of isoprene data and carbon monoxide star data. I construct a 50 mode 50 mode truncated POD, and these projections are on the second set of panels here. And then I compute 50 sensor locations based on the method I just described. For isoprene data, these seem to be localized around the coastal regions, whereas for the carbon monoxide, they're localized over the land regions. And this is the reconstructed results from those past sensors. And as we can see, it does a pretty good job of matching up to both the POD reconstruction that is dense and as well as the data, original data. And just with 50 modes and 50 sensors, these are the results we get. Then I oversample by placing 200 sensors with those 50 modes, and I compute those sensor locations. And I'm still able to find a pretty good reconstruction of the data. Here, some of the final features are defined by the 200 sensors since we have extra sensors to leverage. Then I computed the mean relative error versus the modes or sensors to see how well it does. I picked 500 randomly selected reconstruction snapshots, that is from data that it's already seen, the POD is already seen. And then I picked 500 randomly selected test data that the POD hadn't seen at all. I see that the error goes down exponentially as we increase the number of modes and sensors for the reconstruction results. For the tendency that is slightly slower, decays slightly slower, it only starts peaking when we reach the optimal R, truncation rank R for that chemical species. And the test data, on the other hand, does not show any reduction in error. It just pretty much stays constant, no matter how many modes I increase up to or how many sensors I use. So I'm not able to reconstruct unseen data as well. So to see what's happening inside, we further investigate by picking 500 linearly time-ordered samples and seeing this is the last reconstruction result. And from then on, we see that as we increase time, the error sharply increases for some of the chemical species, and then it stays about the same. So the number of days that I'm testing away from the last reconstruction time snapshot does affect my test results. So sorry, what I did was also, I did not include this in for interest of time, but what I did was implement a incremental update to the PHI-R, the spatial matrix library of POD modes before computing the sensor locations. And this update was made only using the point measurements. So using these point measurements, I updated my spatial modes and then computed my sensors, and I saw a significant reduction in errors, but I haven't had time to explore it further. Finally, we played around with cross-sensing the chemical species, by which I mean I compute the sensor locations for one of the chemical species, and I measure the other chemical species at these locations to see if I can reconstruct those as well. And for example, here I've shown for the ozone sensors, I placed the sensors using the ozone data at the surface, the start data, and I measured and found out the error for the rest of the chemical species and the tendency for ozone using those sensor locations. And I noticed that carbon monoxide also has very low errors. And when I plotted this out to see what's happening at the surface for a random time snapshot, I saw that the sensors for ozone also pick up the prominent features in the data. So it's able to reconstruct the carbon monoxide data very well. So we can use the same set of sensors for both the chemical species. And so in summary, I performed data diagnostics by isolating low order dynamics. I built accurate and computationally tractable reduced order model using the optimized DMD to reconstruct the high dimensional nonlinear dynamical system and predict future states. And I identified optimal geographical locations to determine sensor placement for sparse representation of spatial patterns. And the data-driven analysis has never been applied to simulation data of atmospheric chemistry at this scale. Thank you.